That's okay. Good.
Yeah, exactly. Yeah, thank you so much for managing the program.
The session is Hiroshi Otomo is going to tell us about multiple model of the hydrodynamic equations in the phase flow with hydrogen. Please.
Sure. So in this talk, I talked about the hydrodynamic equation, that's Boltzmann model for multi-phase flow with a large density ratio. So I think multi-phase flow, for solving the multi-phase flow with high density ratio, I think the solution with a phase field model now is a promising approach because it's very robust. And then in that approach, I think common way is to solve the two distribution function. One is the order parameter, and the second is the hydrodynamic equation. And the hydrodynamic equation, the macroscopic one, looks like this. And then I think so that is Boltzmann model have to be construct so that they are reproduced in asymptotic way. So in the leading order, at least they should be derived from lattice Boltzmann equation. So that's why if we ignore all high order term, there are many possibilities to construct a lattice Boltzmann method, lattice Boltzmann model. So some of very famous example here, the two scheme are already published, and the one is the momentum-based scheme and published first, and then that method, the zeroth order moment of equilibrium state leads to pressure, and the first moment of equilibrium state is momentum. So yeah, on the other hand, the velocity-based scheme, also the zeroth order equilibrium state is a p over rho t, and then first moment is a u, the velocity. So, so we would like to point out the sum of formulation here, the rho and the p over rho t. So actually, both of them are derived by same macroscopic equation as we showed in the first slide, but the high order term are different. Actually, they cause some problem in some cases. So that's we want to show here. So first case, the momentum-based scheme. So as we mentioned that the first moment is leads to low U momentum. So according to the Chapman-Scott-Taylor expansion method, whatever we can expect that this kind of term can be seen in the truncation error term. So N is a kind of more than 2 high order term because, and then this term is naively includes, this term because of chain rule, So actually this kind of term caused the problem. For example, the shear force, so this is a multi-phase positive flow case, and the left-hand side is filled by water, right-hand side air. We have some like issue the velocity profile with original scheme. So we try to handle this issue with a high order correction, and then we got this red curve. So that's good. Actually, by the way, this issue is only can be observed in the gravity driving scheme, gravity driving flow, and not observe the pressure driving flow. So because of analytic solution difference. So so that's good. But as you see here, this issue obviously causes the problem in the Galilei invariance. So that's why if we simulate like a dynamic droplet, after a long time step, we got this kind of distorted droplet. So that's why this term causes some of issue, in some cases. A similar way, the velocity-based issue is it should be good and it should avoid this kind of issue. However, the zeroth moment is derived related to the P over rho t, and then that's should outcome this kind of truncation error term. So as a result, we have this term. So this term actually causes the absolute pressure value dependence. So because of this term, So because we assume the pseudo incompressive scheme, so that's why absolute pressure value dependence is not desirable. So, for example, we simulate the static droplets with a very high ambient pressure, like a 1 lattice unit pressure. Then we got a kind of distorted droplet. It may depend on the surface tension model, but this is the example we observe this kind of issue. So we would like to solve this issue. So in order to do that, firstly, I think we agree to go with a velocity-based scheme. But we would like to remove this pressure dependence. Probably we can put some like characteristic density instead of it. But if we simply do that, we likely face some instability. So I don't know, that may be the reason people don't formulate like that way. And then we defer the previous study that based on the lattice kinetic scheme that published by them. And then the formulation seemed to be like this way. So they actually solved based on the macroscopic quantity, like a pressure and velocity. But if we regard this equation as the zeroth moment of lattice-Boltzmann equation and this term as the first moment of lattice-Boltzmann equation, we can map this formulation to the lattice-Boltzmann equation. And then, so that's a promising way because we can implement a lot of recent enhancement of the academic study. But the one issue is that they introduce some iteration step here because of enhancing the stability. So actually, this iteration step is not desirable for the optimize the algorithm because to introduce it, we have to break some do loop because all of lattice-Boltzmann scheme have to be locally. But we have to compute like a gradient or difference neighboring things. So we have to terminate the do loop at that point, and then again, we have to reduce the do loop after that whole iteration. So we want to avoid it, and then also we have some inefficient term here that it requires a second do loop for computing this term. So we try to simplify it after picking up some essence of this formulation. So yeah, this is summary of what we did. So we try to map the previous study scheme to the generic lattice-Boltzmann by after simplifying all the things. And then we try to avoid the iteration step. And then, but to maintain the stability, we implement the collision operator scheme here. By the way, this stability happen when we try to keep the sound speed over is 1 over root square 3. If we can reduce the sound speed, yes, we can maintain the stability, but that's caused the other issues. So we would like to keep the sound speed 1 over root square 3. So this is our model. So I think this P formulation is coming from the previous study scheme, and then especially this KI formulation is coming from their scheme. And then now is the zeroth moment of equilibrium state is simply proportional to P, and not P over rho. So also the first moment of equilibrium state is simply U is coming from here. So they should avoid the issue we mentioned at first of this talk. So we also introduced a filter collision operator. And then we have already confirmed that this equation can be derived at the leading order. Yeah, so for this test cases, we just use the Ahrenkamp equation, which following the original paper. So we just show the sum of validation case. So firstly, static droplet case, with a high ambient initial pressure, like a 1 lattice unit. Originally, we got this circular square droplet, but now we can get a circular droplet, and the Laplace law achieves the expected value. Surface tension got the expected value, and the dynamic contact, the dynamic droplet compared to the original momentum-based scheme, we can get the circular shape droplet, and then pressure and the velocity are pretty constant. So in this case, we apply the x velocity everywhere. So from the Galilei invariance point of view, so we should have a constant value. So that's consistent with that intuition. And also the Poisson flow case, the left half is filled by water. So with that high order correction term, new scheme can achieve the accurate result comparable with the analytic solution than previous momentum-based scheme with correction. Yeah. Also, this is a droplet collision case. So qualitatively, we can reproduce the comparable result with the experiment. And actually, the high order term also sometimes leads hyperbolic, hyperviscosity thing. So in that case, some cases, it's very hard to get this kind of split velocity, but new scheme can work well for that point. Yeah. Also, this is a droplet bubble rising case, and then the result we can get a comparable result with other software simulation. The resolution or something, the other detailed things are not much, but qualitatively it looks yeah, reasonable. So this is a dam breaking case with obstacle. Let me see. I wanna, yeah. So as we see some like more dissipative phenomena after hitting the obstacle here with a momentum-based scheme. But the current scheme, we have a much more like a obvious splashing pattern. So this is because we observe some dissipation around the interface. So this is soon after hitting the obstacle. So actually here the water here, water is shaped like this way. So it is a velocity profile. So right one is a momentum-based scheme and the current one is the present. So actually because of high order term proportional to density gradient, I think this case is drives air, pushing the air more with water. So that's why we may see that more dissipative and result with the previous scheme. So this is a pressure probe result. So we have a pressure probe in the obstacle here. So black one is the experimental result, and then red one is the present current result, and then blue one is the previous momentum scheme result. The velocity scheme a little bit better result than the momentum-based scheme. I think that because that the dissipation things improved. And then I think mostly experiment is matched. I think we some delay here, but that's maybe cause the resolution. So we have confirmed that with the increased resolution, we can improve the result more. And then this is the water height, similarly compared with the experiment and previous scheme. And then similarly, the current scheme showed better results, little better result with than the previous scheme. And then we have some delay. Yeah. Yeah. So yeah, I think that's it. Oh.
Any question? Maybe I'll ask one.
Yeah.
So it seems the approach is actually improved quite a bit. Have you actually compared with other approaches that still have high density ratio? Because in addition to this approach, there are also other disposable schemes that have high density ratio.
Yeah. So we tried a lot of model, and then finally end up using this model. Especially but this talk we focus on hydrodynamic equation part, not talk about a phase field equation part. So if we talk about hydrodynamic part, yes, yeah, at least we tried a momentum based and velocity based scheme. Yeah.
That's for its velocity that we have to use.
Yeah. That we got in the dynamic case. Yeah, I think the static droplet case, the sparse velocity is not much difference. Yeah, between two. Yeah.
Okay. Any other question or comment? No, if not, then let's thank. Okay.
Thank you very much. Yes. Yes.
So our second speaker is Luis. So
That's it.
Luis Eduardo, sure I can pronounce your name. Lucia.
Yes.
Okay, good. Yeah, he's going to tell us about consistency of pseudo potential at the Boltzmann method. So Luis, please.
Hello, everyone. Thank you very much for the introduction. So today I will talk about the consistency of the pseudo-potential Lattice-Boltzmann methods. First, I will do a disclaimer, small disclaimer. So when we talk about consistency, so since we have a broad audience here, usually the mathematical definition, we say that we have a numerical method, and with this numerical method, we want to solve a partial differential equation. So if you pick the solution of the partial differential equation and replace in the numerical method, and then subtract again by the partial differential equation, we will get the truncation errors. So a method that's consistent is a method where the truncation errors goes to 0 when we increase the resolution, basically. So I can start here. So I will start talk about what we can find already in the literature. So I came with this work of Tsai and co-authors. So they were doing a study that was not related with consistency, but they were doing a benchmark in their study, and they did the simulation of a droplet impact in a liquid film with different grid resolutions. And basically what they did, they considered that the Reynolds number was the most important parameter in this case. So basically you increase the grid resolution, probably they reduce the velocity, the impact velocity, and maintain the same Reynolds number. So this is already done for a long time in the literature. You define the dimensionless numbers that are important, you increase the grid, and then you adjust the other parameters to maintain the same resolution. But most of the times, people were doing that, maintaining the same equation of state. Then Alfredo Jaramillo and co-authors, they argued that this procedure was wrong. So they did a boiling simulation with this kind of increase of resolution, and they show that you get completely different behavior, boiling behavior. Because if you just maintain your equation of state, we don't change the parameters of equation of state, it means that your physical equation of state is changing. So if you want to maintain your physical equation of state, you have to change in each, for each grid, you have to change the parameters of your equation of state, so you can maintain the same physical equation of state for all the grids. So I believe that I have more to bring to this field. So in the work of Jaramillo, so basically, so they just talk about maintain the same equation of state for different grids, but then they argue that it would be difficult to know what would happen with the surface tension or with the parameters that adjust the Maxwell rule for the pseudopotential method. So you have to do simulations for each grid, like an experimental work, and find these parameters. So for each grid, you do several simulations, find which is the value of the surface tension, which parameter fits this surface tension, and okay, I think we can improve this procedure. So in this work, I show, first I will define what's diffuse interface limit, sharp interface limit, and I will show how to obtain, how to make the pseudopotential method consistent for both cases. So let me do this definition. When we are working with a diffuse interface method, we have to start with a partial differential equation that creates a diffuse interface system. So first I start with a partial differential equation. These partial differential equations are usually known for the free energy method. Then we define a numerical method, and then we start to increase the grid resolution to solve this partial differential equation. So in this case, we are not changing our interface. We are just increasing the amount of grids. So in this case, we are doing a kind of increase of grid resolution, a grid refinement, where we are not changing the partial differential equation. So this is the diffuse interface limit. What also is very, we can see a lot in the literature, is we want to have a smaller interface to decrease some kinds of errors related with this interface thickness. So in this case, it's not the consistency of the numerical method. What we have to do is to change the partial differential equation to achieve a partial differential equation where the interface thickness is smaller. So this is not related necessarily with the numerical method, it's related with the partial differential equation. But when we do this, we have to know that we are changing the partial differential equation. Each PDE is not the same as before. And it's not just change a simple parameter, because let's say we change the interface width, sometimes we change also the surface tension. And then we have to change the equation of state to maintain the same surface tension. So, and if we're changing the equation of state all the times, what will happen in the limit? We will approach which kind of simulation? So I think these are questions that we need to solve. So what is the PDE for the pseudopotential method? So this is the first question. This is well known for the free energy methods. We have or the chemical potential that we use, or we have a certain kind of Korteweg type of pressure tensor. Maybe this question is a little bit more difficult to solve for the pseudopotential method. And usually this happens because when we see a literature work with the pseudopotential methods, we not start with the partial differential equation that we want to solve. We just start talking, we are going to apply the Shansheng force. But the Shansheng force is already a numerical method, it's not a partial differential equation. And then if we expand this and try to find what kind of partial differential equation we are solving, we see that we arrive in a pressure tensor that's highly dependent on the grid size, because we already start with a numerical method. So we have dependence on delta X. The phi parameter also depends on CS squared. CS squared is also depending on the grid resolution. So we have a partial differential equation that changes. So we are not solving one specific partial differential equation for several grids. We are changing the PD with each grid. So I will talk about two approaches. The first one, I will show what was my first thought about that topic, and then I will show something that I think it's better later. So the first thing that I try to do is to eliminate completely the dependence of the PDE in respect of the grid resolution. So I had to define phi of reference where I defined C as a square that was invariant in physical units. So it's not anymore C as a square 1 divided by 3 in lattice units. I change it by each. So I change C as a square, not the C as a square, that's the sound speed. This is just in the phi definition. But to do that numerically, I have to eliminate all that terms that have phi and replace by new terms this phi ref. And then I have to add more terms in the equation to have more flexibility to incorporate this delta x inside the coefficients and completely eliminate this dependence. Yeah, okay, so this approach seems a little bit drastic, like I have to perform several modifications, and would be better to maintain the original formulation of the method. So if we think about a diffusive scaling, what happens here in phi? In a diffusive scaling, so delta t changes proportional to delta x squared. So it means that the CS is growing to the infinity as we increase delta x, which means that this term here will become dominant inside phi. So actually this equation in the limit, so the pseudo potential, so another approach is to consider that this will be the partial differential equation of the pseudo potential method, where we have the square root of rho actually, as instead of a phi that's dependent on the grid. So, but this approach, I thought about this more recently. So what I explored more was the first one. So I will show the results. The methods were implemented in the OpenLB, the open source Lattice-Boltzmann code. So the first thing, I did a simple planar interface test. Usually we do a lot of simulations and then we try to find which are these, for example, parameters here that fits the densities for the values that we want, that usually are obtained from the Maxwell equal area rule. But since now we have a PDE, that's not actually this one, is this one. Since we have a PDE, I can just compute this from this PDE. I don't need to do any simulation. We can compute all the parameters for surface tension, also to obtain the coexistence, so I don't need to do any simulation. And I can, in the end, just test if these parameters will return me the desired densities. And then we can see that when I do this planar interface simulation with several grids, the densities tends to the value of reference that I want to impose proportional to delta x squared. So the order of convergence for this test was second order. Here I did a droplet simulation. I increased the grid resolution, and then we observed that the spurious currents for the pseudo potential method decrease with order delta x squared with the grid. I also did the two-phase flow between parallel plates. So we have two different phases. And again, so this is not the solution considering a sharp interface, is already a solution for a diffuse interface. But again, when we increase the grid, we converge to the correct solution. And also there is a lot of more tests that we need to explore. Well, this consistency, but I will talk also about the sharp interface limit. So my idea was to talk just about the diffuse interface limit in this talk. But recently I have some thoughts about this sharp interface limit. And I think that they are interesting to present today. So basically, okay, here we have a problem. We are changing the equation of state at each simulation. So for example, I want to simulate this, but I cannot create a PDE that have almost zero interface width because my interface cannot be smaller than delta x, than like the distance between two lattices. So my interface is limited by my resolution. So it's natural that I will just be able to decrease the interface when I increase the grid resolution. But I want to see, so the question is to where I go when I do this type of change here, when I try to decrease. Like usually when we want to model the standard approach would be consider that each phase is modeled by the Navier-Stokes equations, and then define the jump conditions for the interface. If we have phase change, we could define some kind of phase change model. So this would be, for example, the standard approach where we would discretize these equations by finite volume. And what I was thinking is, if when we do this change, our partial differential equation goes to the same result as when we solve this problem, for example, in the standard methods, when we just model them by incompressible Navier-Stokes equations, then I did here a dimensional analysis considering some important properties of the fluids. I considered that we are in the diffuse scaling. And also, I considered that in this case, in the sharp interface limit, we don't want to change necessarily the equation of state, because we want to maintain in lattice units, we want to maintain the interface with the same size. We want to increase the size of our system, but we want to keep the interface with the same size. So performing the dimensional analysis, considering this, we obtained that the lattice surface tension should be proportional to delta X with the physical surface tension. But there is something interesting here. If we do this, we notice that our physical pressure increases. So our physical pressure is proportional to the lattice pressure that now is invariant because we are keeping the same equation of state in lattice units. But it's the lattice pressure divided by delta X squared. So it means that this goes to infinity in the sharp interface limit, which means that the Mach number decreases proportional to delta X squared. So we are approaching a case, an incompressible case. And also we can think about, if we have a system with a certain temperature, we will have like equilibrium pressure, so we have like, let's say that we have a droplet, we have two fluids at a certain temperature in equilibrium with a certain pressure. If this pressure is going to infinity, it means that all pressure variations of our system that are a result of the surface tension or results of the flow, the viscosity of the flow, this means that all this pressure will have less and less influence, because all these pressure gradients will become irrelevant in comparison with this new equilibrium pressure. So our system will tend to an equilibrium situation. And also I show here, so we can obtain we will obtain a consistent method if we change kappa proportionally, like 1 minus kappa proportional to delta X. So I show here what happens when we do this sharp interface limit. So I start with a simulation, a droplet, and then I start to increase, like I maintain the same interface thickness in lattice units, but increase the distance. So my interface in physical units is getting smaller. So what happens is that the pressure of my system will tend to the saturation pressure. So usually to the Laplace equation, we have like the vapor pressure would be equal to the saturation pressure, and it depends on the surface tension and also of the radius. But my radius is growing in lattice units, my surface tension is decreasing in lattice units, and I am maintaining the same saturation pressure in lattice units. So this means that these terms goes to zero, and the phase density should go to a planar interface. My phase density should go to a planar interface, to the planar interface densities. And I show here that actually the densities of the droplet converge to the planar interface densities, but now actually with convergence actually smaller than 1. Here I compute the L1 norm to the entire system and converge with delta X. I also did this test for the spurious currents, but now different from with the diffuse interface limit, the spurious currents grow with time. I believe that this is happening since we are not changing the equation of state in lattice units. I'm not sure completely what's the parameters that most influence the spurious currents, but I noticed that they were not changing in lattice units. If I maintain the same equation of state, even if I was changing the size of the system, the spurious currents were constant. But since we are in the diffusive scaling, the physical velocity is proportional to the lattice velocity divided by delta x, which means that for when I increase the grid, the spurious currents goes for this grid. So the conclusion is also that we have to combine both approaches to actually converge these spurious currents to zero. So the conclusions were that for the diffuse interface limit, I obtained error proportional to delta x squared for the benchmarks that I test here. The error for the sharp interface was delta x in the case of the dense profile, but the spurious currents were growing to infinity. And that's all. And I also, for people that get interested in the OpenLB, that was the software that I used to do these simulations, we invite for the Spring School. Thank you.
So you consider to do your analysis in the Kahn number, so in terms of physical size of your interface, the ratio between the size of the interface and the grid spacing.
Yes.
That may be a natural way.
Yeah.
For analyzing that.
Yes. So, and what would happen here is that in the diffuse interface approach would be the same as maintain the Kahn number constant, and the sharp interface limit would be make it to zero. Yeah.
Okay.
Yeah.
Maybe we have time for one quick question if there's any. No, if not, let's thank Luis once again.
Thank you very much.
Okay, so our third speaker is by Shinpei Saito.
Yeah.
And he's going to tell us about thermodynamically consistent chemical potential-based free energy lattice Boltzmann model inspired by color gradient and time-wise equilibrium. So Shinpei, when you're ready. Thanks.
Okay. Yes, I pushed it. Thank you for kind introduction and thank you for coming to my talk. My name is Shinpei Saito from AIST Japan. Going to talk about chemical potential based free energy lattice Boltzmann model strategy, but most of my talk is devoted to the color gradient lattice Boltzmann equilibrium, because it is very important to describe what I have to say. Okay, then let us start my talk. As you know, there are several lattice Boltzmann models, including the color gradient, pseudo-potential, free energy, and phase field. This kind of classification is not comprehensive, but I use this kind of classifications. And in this talk, I focus on the color gradient model from Gunstenson et al. And the free energy model from Swift et al. Here I show several applications of the color gradient lattice Boltzmann model, including the from left to right, the jet breakup in liquid, and the droplet on the solid surface, improved wetting boundary condition implementation, and the multi-phase flows in porous media, and so on. This kind of color gradient model has several advantages in the lattice Boltzmann phase models, including there is no prior computation of interfacial tension, which is directly given as volume of fluid like ideas. And very small droplet or bubbles can be kept in characteristic of color gradient, and the high viscosity ratio can be easily obtained and easily extends extendable to multi-component system, which is also straightforward. And recent advances, this talk is not devoted to this topic, but recently the relationship between the recoloring algorithms and the Allen-Kahn equation is discussed, and the some development about high-density ratio applications and the introduction of surfactant effect is also now under development and recent advances of the color gradient. Our focus in this talk is the equilibrium distribution function equilibria for the color gradient light spot models. Okay, basically in the color gradient, two kind of distribution functions are introduced to distinguish the two phases. Basically, one phase is called red colored distribution function, and blue colored distribution function are commonly used to distinguish two phases. And they, in order to keep the pressure at the interface, several modification is done to the equilibrium distribution functions in the common way. Can I use a stick there? Okay. Here. Is it?
Yeah.
Okay. Basically, in the color gradient strategies, the zeroth order part of the equilibrium distribution function is usually slightly modified from the original one. Here, the several modification has been done, and when the phi, this term is corresponds to the usual lattice weights, which reduces to the usual equilibrium distribution functions for single phase flows. But this term defines the different speed of sounds for each phase, and here I show the several moments, including the zeroth order, zeroth first, second, and third order moment is shown here. The underlying issues in the color gradient lattice Boltzmann as can be by using the second order moment and third order moment, and I didn't show the exact procedure, but by using the Chapman and Skog expansions, the macroscopic equations have error term as shown here. If the density ratio of two phases is unity, there is this term will distinguish. This term cannot be appeared, but usually there is a density ratios between the two fluids, and so this term cannot negligible for common cases. This kind of error terms is essentially included for the color gradient. So the discrepancy between the analytical solution will be occurred due to these error terms. Here, what we do is to improve the effect of these error terms, we derived an equilibrium distribution function to cancel this effect to the error term and show the model. So the developed model reduces to a simple form in the space of the so-called central moment space, different from the phase space usually used in the lattice Boltzmann. And we applied the free this kind of equilibria to the free energy lattice Boltzmann model at finally. Okay, first we show what the moment used in the lattice Boltzmann is. Here, by transforming the dfs in the LBM into the moments and perform the collision operations for each moment, which is usually called MRT collision. In a common way, the raw or natural moment is used for the MRT lattice Boltzmann. The moment is defined like this. The central moment is also the one of the moments defined in this kind of approach, and the definition is as shown here. The macroscopic velocity appears in the definition of the moment, and this is the present focus of my talk. In this talk, we use the D3Q27 lattice model, so 27 moments is resulted. Okay, then original color gradient equilibrium df, as shown here. the 0th to 2nd order moments are, we show the central equilibrium central moments will be shown from now on. And the 0th to 2nd are shown like this. And we focus on the 3rd and higher order moments from now on. By using the distribution equilibrium DFs, the 3rd and higher moment can be shown here. And as you can see, there are several velocity-dependent time here and here. This kind of velocity-dependent term will remain for equilibrium central moments for the adapting the color gradient to equilibrium DFs. And here I introduce a work done by De Rossi and Luo for the single phase flows, but when the D3Q27 lattice, the equilibrium DF is represented by the aramid expansion up to 6th order. The nth order velocity component vanishes from the equilibrium when transformed into the central moments. So according to this work, let us apply the 6th order aramid expansions to the equilibrium DF to the CG models. I mean, the here you can see the up to 2nd order. So just adding the additional order by using aramid polynomials up to 6th order. As a result, several velocity-dependent terms, were vanishes, but there still remains this kind of terms in the equilibrium central moments on the 3rd and higher order moments. So we additionally improved the equilibrium for color gradient. Here we divided into the equilibrium DF to 2 parts. The first one is the commonly used for single phase flows, similar to the single phase flows one. And we used is here by using the aramid expansions up to 6th order, we express the first term, right under this term, up to 6th order. And by using the pressure minus rho CS proportional terms, we derived an additional term to correct for the error terms in the CG models. By using this kind of approach, the term you can see here is represented by this kind of expressions by using aramid polynomials defined here. So by applying this kind of corrected equilibria in the central moment space, as you can see here, most of the moments reduces to 0, and only the 2nd, 4th, and 6th order moment becomes non-zero component, which is very quite similar to the one for the single phase flow modeling. Okay, very becomes simplified form, and it seems to be implementation is also simply. Several numerical tests will be shown from now on. The layer for the flow is shown here. The setup is from the references over there. And by using this kind of setup, the body force is acted from left to right. And the analytical profile is expected only by the 6th order equilibrium and correction. This kind of modified one only agreed with the analytical solutions. In addition to the 2D problem, here you can see the 3-dimensional radial instability, which is one due to according to the gravity, gravitational interfacial instability. The left one is the original, and the corrected one is shown in green. And several components should be compared with each other, including bubble, saddle, and spike. And our results well agreed with the several numerical simulations, including the improved color gradient proposed by Wen et al. And the multi-phase lattice Boltzmann black solvers. Okay, I devoted most of the time for color gradient, but from now on, I talk about the free energy model, application of this equilibria to the free energy model. Yes, here we show the chemical potential-based free energy model recently proposed by the Chin Lee et al. In the free energy LB based on the chemical potentials, there are several similar problems are still underlying as color gradient lattice Boltzmann. The equilibrium is slightly corrected. According to this, several problems can be seen in the free energy model, several free energy model. And the thermodynamic consistency determines the accuracy of the gas-liquid separation, phase separation in a class of free energy. Lee et al. Proposed the alternative scheme for achieving thermodynamic consistency with the use of aromatic expansions up to third orders. Okay, here we use the van der Waals type non-ideal regulation of state. And the time, its chemical potential can be written analytically as shown here. And in the original free energy model, the force vector can be written as this, in a framework of potential form. In the strategy of Chin Lee et al., the force is replaced by using modified pressure, and as a result, this kind of force vector can be redefined. And by using this Lee et al.'s free energy model, we apply the similar approach to the equilibrium distribution functions. Here is the single phase equilibrium distribution function up to 6th order, and the right side is additional correction terms. As a result, as a similar manner, as a similar way, as seen in the color gradient, as you can see, only the several even moments have non-zero terms, and other equilibrium central moments are no longer velocity dependent. So for this case, the equilibrium central moment becomes quite simplified form and easy to perform too. And finally, I show the thermodynamic consistency of the present free energy model. According to the theory, the thermodynamic free energy model can reproduce the thermodynamic consistent results without any tuning parameters. And here I show the green plot reproduces a present free energy model, and the original free energy model is reproduced by the symbol here. As can be seen, the standard FE model, very near the critical point, the thermodynamic consistency can be recovered, but as the temperature decreases, the thermodynamic consistency, there can be seen the discrepancy between them. On the other hand, the present free energy model can be, the thermodynamic consistency can be kept at the lower temperatures. This is the last one. And okay, let me summarize my talk. In the color gradient, we propose a generalized form of the equilibrium distribution functions, and its central moments looks like the very simplified form, so it's easy to implement. And this kind of generalized one can be applicable to the several free energy models. And the simulation result says that the thermodynamic consistent phase separation can be achieved by using this free energy model based on the color gradient generalized equilibria. Okay, that's it. Thank you.
Do we have questions?
What was the lowest reduced temperature that you were able to achieve, or if you had some limitation in terms of stability?
Okay, for this case, and it is strongly depending on the parameter A, which is affect the interface of width, and we choose the A as shown here, 9/392. In this case, the achievable reduced temperature is like here, 0.7. By using more widened interface, more lower case should be done, I guess.
Maybe I'll ask a question. So, I mean, this is really nice that you can get better like thermodynamic consistency at lower temperature. Have you ever compared anything to do with dynamics? For example, with the standard energy model, often depending on the velocity of the motion, then the density might actually shift a little bit. Do you actually see this problem with the present with the new model?
Okay, thank you so much for your comment. The answer is no. I'm still working on the static case. So this kind of flat interface case, so that kind of dynamic case should be done in the future for my study. Thank you.
Okay, so let's thank.
Then it must be green, okay. Yeah. Okay, I believe these things are recorded, so you don't see with the stick.
That's true.
So maybe I'll just not use it. Okay, is there?
Our next speaker is Martin Gaius. Very exciting. So he can tell us about sharp interface-to-face cumulant lattice Boltzmann model. So Martin, whenever
Yeah. Whenever the recording has been started, because we are now using PowerPoint, let us see whether I have to hurry up a little because I have to catch a train. Yeah? Everybody before me used a PDF apparently. So now we get started. Thank you very much. So okay, so I put the, as I said, can I already move it? Yes, I can already move it. So I put my funding agency in front. So the motivation for what we are talking about, let me see whether this is going started, is that we want to print concrete, which means we have fluids with a high density ratio and with a high viscosity ratio. Yeah, and this requires us to use actually to be able to model in the same simulation things with different orders of magnitude different viscosities and orders of the magnitudes different densities, and this is kind of challenging, as you know, and this is why we always switch our model and look for something better. So first of all, there are a few students potentially present. I make some advertisement that I'm teaching a lattice Boltzmann course, and this is online. So if you want to take a picture of this, you can listen to my talk. So to my lecture, 20 hours of lattice Boltzmann. Yeah, this is not. This is here. Few minutes. Oh, it's messed up because we're using a different computer. So I'm starting with talking about cumulants. I actually take precedent that I was introducing central moments to a lattice Boltzmann, and I always used sixth order equilibrium from the very beginning, but I'm not using this anymore So there's a better solution that is called cumulants, and cumulants are quantities that, in addition to being Galilean invariant, are also independent of each other. Otherwise, we use a similar lattice, and then we use 27 degrees of freedom, and then we have these cumulants, and cumulants can all relax at the same independently. So let me see whether all of the rest is also messed up. So benefits of cumulants, there were not so many cumulants talks in this conference. They are like central moments, they are Galilean invariant, but in addition to this, they are a weighted orthogonal basis, so they're Galilean invariant and like Hamid polynomials, but also with reference to they are more orthogonal than also in the non-equilibrium, they are orthogonal, whereas Hamid polynomials, there will only be an equilibrium orthogonal to each other. And what I consider the most important part is that with this kind of MRT model, we have an analytical solution for the optimal relaxation rates that give you first order accuracy. So whenever I come to these conferences for a long time, MRT, we don't want to use MRT because we don't know what are the relaxation rates. Here we know what are the relaxation rates, because I've written them down here. This is the strange solution. This comes out, and this is the solution. And with this solution, there are several things that I believe have first been shown. And with this model, like here on the top, we can simulate the track crisis. So I believe this was first shown with around the sphere. So this convergence of the track, and we also showed the bottleneck effect in isotropic turbulence recently. Okay, and this had, this can then be applied to any sorts of large-scale simulation. So how I'm doing is time. I've already spent 5 minutes on not saying anything about multi-phase flow. The thing is, whenever we want to combine this with phase field stuff, so you may be able to do high density ratio stuff, but you're losing this property. So it's not easy to keep first order accuracy. I mean, in the interface, of course not, but the dynamic that we've come used to with this. So, and now I've been talking a lot about cumulants, and you thought you probably came here for something else. I don't know, maybe you came here for seeing this. I don't know. I'm sorry for the resolution. These are the best pictures that I could take, because I guess we had this the cheapest tickets on Earth for this. But I have to say that there's like with cumulants, because once you have this kind of event like on Wednesday that we had here, future conferences will have a difficult part to keep up with this social event. Unfortunately, there was a limited number of tickets.
But we didn't have the money.
Okay. Sorry. So this is as far as I could, as close as I could get. So let's swiftly come to our tailored model here. This was already introduced in some of the previous talks. We use a phase field model together with Abbas Fakhari. So this uses a central moment approach to determine for liquid phase with when the phase indicator is equal to 1, and the gas phase when the phase indicator is equal to 0. So this is the classical stuff. And now we run a little bit into the problems that have been discussed already in the first talk. So I can potentially make this brief. So originally, lattice-Boltzmann, uses a momentum formulation, where the first moment is actually the momentum. And this, when you have a high density ratio, leads to the problem that you have in the interface, you have a very strong gradient in the moment in the velocities. Yeah, so this gives you a big problem. Or in the first moment. So one of the ideas that is also used is to go to a velocity formulation. And kind of a little bit naive, we assumed that velocity formulation solves everything. Yeah, so unfortunately, this is not true, because here in the velocity formulation, as we have seen already in the first talk this session, we get the problem with the scaled pressure. Yeah, so we don't have pressure here, we have scaled pressure. And when we want to have the pressure in both phases being the same or very similar, then because we have to divide by the density, we get in the interface, we get the high gradient in the scaled pressure. So now, as you said, you always have to die one death or the other. Yeah. So it depends on what you like more. I think usually we like problems in pressure more, because in velocity this is very convoluted. Yeah. So we have many different derivatives here. So we go for the velocity formulation. But now we do it a little bit different. So we still use these phase field methods, but we apply it in a way of a sharp interface model. So it's not a volume of fluid, but it's the same phase field method. But what we do now, instead of having a transition from gas to liquid, we said that at phi a equal to 1/2, so in between these two limits, we set a contour, and this contour indicates for each node whether it's in the liquid phase or in the gas phase. So we identify you are larger, the phase field is larger than 1/2, then you are liquid. It's lower than 1/2, you are gas. And so the problem of because we want to keep everything outside our nice, cumulant equation. So we want to keep this as it is and have the two-phase problem only as a sort of boundary condition problem. Yeah. So because this, of course, means we have to set boundaries wherever we cross the interface. So basically, this looks like this. So this is the lattice-Boltzmann method. There's a collision and there's a streaming, and then instead of now the streaming, we set the boundary condition, yeah, where we have gas-liquid replacement. So there is a so-called interface condition for the liquid and an interface condition for the gas. And the way we do it algorithmically is that we look for the gas nodes that surrounding the interface. So this is why they are both on the same location, and then we replace both parts of that link. Okay, so and now the way this is done is in principle super simple. Yeah, and maybe a little bit too simple, but there's an engineering project. So I thought, okay, let's find an engineering solution to this. We don't actually look where the interface is, but we set the interface always at the center, in between the two nodes, and we have here simple matching conditions. So, and the matching condition is simply that the velocity on both sides is the same. And with the velocity formulation, this means that the one going this way and the one going that way, so and in the opposite direction in the same phase, if you subtract them, you get the velocity on that link, and this must be true for gas and liquid at the same time. So this is one condition, and the other condition is can be interpreted in two different ways, either as a momentum exchange way, but I like to so this is useful to actually show that it's momentum conserving as long but I actually like to interpret it as an as a pressure matching. So scaled pressure matching, this is why we have here to multiply with the densities. So what we do, we can compute the pressure, not now as the difference between these distributions, but the sum of the distribution. This is the total pressure. And since we want to set the static pressure, we subtract the dynamic pressure, where the velocity we measure in the liquid phase, because we believe that the velocity is dominated by the liquid phase. Yeah, so we do this on both sides together with the different densities. And the reason why I prefer to consider this not as a momentum exchange, Galilean invariant momentum exchange condition, but as a pressure condition, is because then I can easily add the Laplace pressure on top of it. Yeah, so the way we have surface tension in here is simply we add the Laplace pressure. Okay, sorry, have you taken your picture? So in the Laplace pressure, this is the only time when we actually consider the distance of the node to the interface, because we calculate because we do all the calculations on the nodes, we can calculate the with some equation that I found in a very old paper, the effective radius of the phase field, because the phase field is everywhere, right? And then this will be the radius from that point to, I mean, the curvature. So we compare it to curvature, and from the curvature we get the effective radius. Yeah, and from this we actually have to subtract the distance to the actual interface. So we compute the distance to the interface, we have the effective radius, and then the curvature radius, and then we subtract it, and then we get the actual radius of the interface, and from this we compute the surface tension. I'm going to have to speed up. So the big part is, of course, we have to, because the interface is moving, we have to reinitialize nodes. And the good thing is that with a little bit of cheating, we can recover most of the directions that we have in the usual way, yeah, by a few assumptions that I'm not going into now. The only thing that we really have to reinitialize is the resting population, and the resting population we get by taking the pressure from the phase with which we want to reinitialize. So we go looking up the neighbors and then make a weighted sum over this. So using the lattice weights and divide by the sum over the weights. And now we recover the pressure there. And from the pressure, we recover the resting distribution. Okay, so unfortunately, I don't have a lot to show in terms of validation. This is a case that in the first talk we also saw there's a rising bubble. Actually, this is pseudo two-dimensional. Actually, there are not so many cases for high density ratio benchmarks. Maybe I'm stupid, but you may help me with what I'm supposed to simulate here. Okay, let's go to a few examples. I don't know whether this was too quick. Now this is actually you have to think this is 10 centimeters by 10 centimeters thing, and it's actually water in air. So it's a small toy that we have here. So there's a dump brake going down, and I have it like this that you could actually see that air is going up. Maybe I'll do it like here, I don't know. So this was, bless you. Now I put like water up here, but I increased the viscosity, decreased the viscosity because I thought it's not turbulent enough. So you see that there's actually air in this. It's not just the liquid going down. Yeah. Okay, so the width of this here is, I think, 64 lattice nodes. Okay, I guess I have taken overtime. I don't know. So yeah, so these things I mean, keeping high density ratio and a lot of viscosity contrast in the same model is challenging. So there's a lot of algorithmic steps which are kind of complicated and which I could not address all of them. I hope this will soon converge into a publication, but I'm still not completely done with this. Yeah, so we are using sometimes people make advertisement for their open source code. We also have an open source code. If you're interested in cumulants, you can download this here. I thought maybe you take a picture of this. Unfortunately, the Sharp interface model is not yet in it, but when it's finished, you will find it there too. And with this, thank you for the music and thank you for your attention.
Yeah, not many things you described. The one thing that catch my eye is the
Yeah.
modification of the streaming.
Yeah.
That I've been thinking a lot because that if we understand the physics of the van der Waals gas, the modification of the streaming
Mhm.
actually is the part responsible for the change of the pressure from the ideal gas.
Mm-hmm.
Ideal gas, the particle goes straight and bounce on the
Yeah. Yeah.
pressure, which is part the van der Waals gas, the particle, because of the interaction force, the attractive force, that actually did not reach the wall and actually comes back.
Yeah.
This is similar to the effects of the interface. And when we made, all of the previous works on the interface, LVM, are basically you apply a force in the equilibrium distribution or in the traditional gradient.
Yeah.
Basically, you apply it one way or the other. And that you did not modify the stream part, which, if you have a high density particle, next to a low density, then you have a very biased distribution after the advection. And then when you do collisions.
Yeah. So I think, yeah.
It's actually when you have a modified streaming.
Yeah.
Right, some particle never really, it just come back, right?
Yeah. So there is.
And so that the equilibrium after the advection part is not that far apart from the desired equilibrium after the advection.
Yes, I believe you can add the forcing in the streaming, and there is, for example, for shallow water equation there is one model that does this, and in particular, because this is now using boundary conditions, yeah, there's always different interpretation of boundary conditions, but my interpretation of boundary conditions usually is, yeah. In principle, physically, forces are not in a collision. Forces would always be in streaming if you think physically. Yeah.
So especially the non-local forces, it appeared on the left-hand side of the Boltzmann equation.
Yeah.
So they should be a part of modifying the streaming process. So the particle does not go like a free particle that just goes straight line with no change of momentum.
I always keep forces out of the collision. Yeah, I think this is.
Collision part, including appropriate force, and
You're implying that force is part of the collision because this is how it's often implemented. Yeah, but It's not the original physics, and it's also not necessarily the way you need to implement it. You can implement the force in a streaming. Yeah.
What I'm saying is, it has to be implemented in terms of modification of the stream.
Yeah. Yes.
And I think also, I mean, many things that this is one part I catch. Perhaps I catch. If you agree.
Thank you. Yeah. It is the modification is in the streaming. That's the point.
Sounds like there are interesting discussions to follow up there.
Yeah. Unfortunately, there's not a lot of following up because I have to go to my train.
Well, looks like we are
Yeah.
about to-
Thank you.
The big name. That, not that one, the next. Yeah. Okay, wait. Was it changed? Because it's not the one. No, wait, that's not the one. Wait, try again. I think they renamed it. Again. Is it the PM? No, it's PPP. There's a couple of changes made. No, it's not this one. I copied it. Look, this should actually. It disappeared. It disappeared, the one that we copied.
Is it an old one or something?
No, that's the old one, that's over there. It's actually in here, you can just take it. from
No,
here.
it's just,
Yeah.
just copy,
Yeah.
just,
Yeah.
we don't even need to copy it, just.
Yeah, just open it from there. I just realized.
There's ice cream in there. Oh, sorry.
We had.
Yeah, we did. Yeah. That's that, is that. And
Come on. Hey, try.
right, good.
Wait, it's just. Yeah, just.
Alright.
Just play it from here. Yeah. So it's this one.
Second, next
No,
one,
the
next
next
one.
one.
Yeah. Yeah.
Okay, so our last speaker, but certainly not the least,
Mhm.
is Ketan from Zakaria, and he's going to tell us about application of novel Boltzmann Euler model partially problem solving. So, Ketan, please.
Thank you for the introduction. Yeah, so as I said, my name is Jitin. I'm coming from the University of Limerick in Ireland. And this talk is going to be about a new Euler representation in lattice Boltzmann, and we're going to try to implement that in bubble columns. So that's my current work right now. So we'll mostly focus on the model and what we have so far on the bubble column, basically. So yeah, so first, I'll skip this one since we don't have much time. Yeah, so why Euler? Well, in my project, we are mostly looking at more industrial problems, which are much more larger scales. So in those large scales, you generally cannot do a proper fully resolved simulation because of the scales involved. Therefore, what is normally used is an Euler, where you don't resolve the interfaces and instead you use a volume averaged equation, and you take the effects of the interfaces into account using various mathematical models. So that kind of model tends to be very simple to implement in Navier-Stokes solvers and also computationally cheap, which makes it very attractive in an industrial standpoint. And so we want to use lattice Boltzmann, where we solve the lattice Boltzmann equation. And by Chapman-Enskog expansion, you get the Navier-Stokes equation. And one of the key advantages here is that you generate your own pressure term, so you don't have to do an iterative solver for the pressure, which is great for the most part in single phase flows because it's highly parallelizable and efficient. But when you go to an Euler equation, that becomes an issue because if you try to go from lattice Boltzmann to Euler by changing the zeroth order moment like this, by adding a volume fraction over there, you get the Navier-Stokes equation to look something like this with a wrong pressure term. You have an extra alpha in there. It's a gradient of alpha times p instead of alpha times gradient of p. This might look like a small fix. You can add a correction term over there, and that has been done. And it works for simple cases. You can add a correction term proportional to pressure times gradient of alpha. But there you are introducing a lot of discretization errors because here the pressure is being calculated, pressure gradient is calculated using the LB stencil, and there's a lot of discretization error leading to a lot of diffusion that's happening. Another approach was by Hawker, I think. Yeah, it was to modify the streaming step to account for the local variation in the volume fraction. And that matches the discretization perfectly. But in our test, we found that to be quite unstable when you have dynamic interfaces. So it's not very useful for more practical situations. Therefore, we need something which is stable and gives the full Euler-Euler equation. So now we will go on to describing the new model. So the new model is a combination of a couple of different variants of LB. So I'll first start by introducing the two different variants, and then going on to creating the new model. The first one is the well-balanced LB, which was created by Guo et al. In 2021 for capturing accurate interfaces. So in his paper, in the first half, he modifies the LB equation in ways similar to this, where if you do a Chapman-Enskog expansion, you get a Navier-Stokes equation which does not have the pressure. So, and in the second half of his paper, he adds the pressure specifically based on the chemical potentials to get really good interfaces. But if you take the first half of it, what we get is a pressure-free lattice-Boltzmann equation, which gives us a blank slate for us to add our own pressure. So looking at this, our first approach was to use two of these well-balanced equations, and you can add your own pressure from a Poisson equation. And that works. We did the solution and it works perfectly fine, but we are removing one of the key advantages of LB, which is the lack of Poisson equation. So we went forward and went back to the slate and we thought about how we can remove the Poisson equation. And for that, we also have to introduce the incompressible LB, which there are many ways of doing this in literature. This is one of the way by he et al., where you modify the equilibrium distribution like this. You get an incompressible form of the Navier-Stokes equation. So these are the two components. So before we get to the final model, we also have to modify the two-fluid equation, Euler-Euler equation a little bit. Firstly, we have to introduce the mixture equation, which you get if you add the two phases or n phases. If you add all the equations, you get the mixture equation where you have a correction term over here to account for the differences. And over here, this contains the pressure term without any correction over here. So this solves for the conservation of the mixture momentum and ensures that there is no divergence in the mixture velocity field. And also we do the phase intensive formulation so that we can remove the dependence of alpha on the equation. And so that's basically you divide everything by alpha times rho, which is the mass, and you get another correction term over here. And you can do the similar thing with the mixture equation as well, and you can combine all the correction terms to one term over here. So basically, you get a set of correction terms. You get a couple of incompressible looking equations, which can be solved. And also we have the well-balanced equation for the gas phase. So now if we combine all of these into a jigsaw puzzle, you get the new model, which starts off with a well-balanced equation for the individual phases. So for the gas phase, for the dispersed phase, and we can combine that with the incompressible phase intensive mixture equation, which solves for the pressure inside this equation. And you can get the pressure from this and feed that to the well-balanced as a input, so as an external force. And additionally, we can do the advection equation for the volume fraction, which as a package deal, it gets the final two-fluid equation without any approximations. Usually you use a mixture equation with an approximate model for the gas phase. Either you assume a slip velocity or you neglect certain terms, but in this case, you should get the full two-fluid equation. So moving on to certain validation cases, I'll quickly go through this. We did some qualitative test cases with one of them was falling swarm of solid particles. So we compared the results qualitatively with some results from literature. We weren't able to get a complete comparison because this isn't a very well done case. So for a more quantitative test case, we did Rayleigh-Taylor in this case at a lower Reynolds number, and we got quite good comparison. And we also we wanted to do it for turbulence because that's the main application for this. So, and that's also a much more complicated situation. So for the turbulent case, we did a turbulent emulsion where you have two fluids. Both of them have the same viscosity and the same density, so no density ratio in this case. And you initiate turbulence using a turbulent forcing scheme spectral by the Alvelius method. And you can see the video over here. Yeah. So the bubble, or it's not a bubble because you don't have an interface, but the swarm gets deformed by the turbulent forcing, and it creates an emulsion, although you can't see the interfaces again. But you can see the effects of it quantitatively when you see the spectra. So the blue line over here is a single phase DNS result, and the red line is the two-phase, emulsion simulation in the DNS using pseudopotential. And the black line over here is our result from the two-fluid model, and it matches very well with the DNS result, which indicates that the physics is being done correctly. So moving to the buoyancy-driven flow, which is the bubble column that we are thinking about, this brings about a lot of other challenges which we did not initially anticipate. Firstly, the geometry is really large. So most of the test cases and experimental cases that we can compare with usually use meters-long bubble columns, so that the scaling becomes quite difficult. And we also have very high density ratio, that is 1,000 ratio. And also, we have the velocity problem, which the gas phase tends to be extremely light, and there's a lot of force going on the gas phase from the buoyancy. So that has to be, in actual physical situation, it's balanced by the drag force. But in practice in LB, the drag force tends to be quite large, and if you don't get a tau value small enough, the delta T is not small enough, and you tend to explode instantly. So that was a problem that we are facing right now, because our tau value is still not small enough to achieve a small enough time step to completely resolve it. So the temporary solution that we thought about right now is to simply assume a pseudo steady state essentially, and relax the velocity towards the terminal velocity by assuming that the coefficients of the drag are constant, which is a strong assumption, but it's the step we chose to test the model out, and we'll be working on that further at this stage. So using this assumption, we are basically relaxing the velocities towards the terminal velocity, which stops it from exploding at the first iteration. So we want to use this to test it with the Becker case, which looks something like this. You have a cuboidal system with an off-center inlet over here, and there's a sparger, and the superficial gas velocity is given over here, and these are the boundary conditions that we use. And we matched most of it with we scaled the system down by 30% to make it a bit more manageable. But we were still not able to match the viscosity a little bit because of a certain fluctuation, which I'll show in the next couple of slides. So the only condition which we were not able to scale properly was the air viscosity. But besides that, we scaled everything down to 30% of the original case. So, okay, this is the results contours from our simulation. You can see the bubble plume, the volume fraction, and you can see that you are getting the expected oscillatory pattern. You can see the expected 3 eddies that are formed. It's a lot more instantaneous because of the LES, and there's a lot of turbulence, so it's not very clear of the statistics of this. So we can plot the probe data. Oh, I forgot about that. There's a probe located right over here at point A. So we measure the local liquid velocity at the probe. And the results for that are shown over here. You can see a clear oscillatory pattern. It comes and goes. Sometimes it becomes complete chaos. And then the next 100 seconds later, it comes back to a proper oscillatory pattern. But to analyze what is the period of this, we can do the spectra. And from our test, we get a range of 35 seconds to about 50 seconds, approximately. I'm not giving a fixed range because we are still trying to match the conditions completely, but in all our tests, it comes around 35 to 50. And in the experimental test, they get a value of 41 seconds. And in RAN simulations from previous researchers, they usually get around 32. And there was also an LES simulation which got around 50, 55. So it's promising to see that we are getting in the correct range of values. And so we are on the right track. But I mentioned the fluctuation. So this is the problem that we're having. Specifically, whenever we have negative or close to negative values of the water velocity and very low masses of the air, we get a lot of fluctuation in the gas velocity, which we are still not entirely sure how to fix this because it's quite a singular problem. We have very low mass and quite high forces. So it's a singularity problem. So we are thinking about applying limiters or stabilizing the model a little bit more so that we can use smaller tau values. So we are looking at all those options, but that's the current state and the next things that we are going to do. Thank you.
So this is single bubble size, right?
I'm sorry? Single bubble size, yes.
So what's the oscillation frequency?
Well, I'm not sure of the exact correlation of it, but it's completely dependent on the drag force. So if the drag force changes, the terminal velocity changes and the pressure changes, and it should. Right now, it's around 1 millimeter, around that range. One. It's a correct. It matches perfectly. I mean, that's the average value that was observed in the experiment. Yes, my original project is about coupling this with a periodic box for small scale and giving a bubble size distribution from that, like a two-way coupling. So that's why we came over here for the two-way. So yeah, we'll be adding more dynamic bubble size determination. It'll be a smooth one. So the idea right now is to get a distribution of the bubble size and input that as an input for this to improve the local conditions. Yeah.
One last time, can I get it again? Before you go, so I think we're going to have a coffee break for about half an hour. And then at 12, there is going to be, I think, the award ceremony and final remarks. I suppose in the lecture theater. So